Sir, did you say anything just now?
No, I just said that everybody's, and then but before you came, he was just Paramala. He was just asking about how to submit the solutions to the assignment 1 problems that I just uploaded this morning. I was going to, I told him that we will put in a submit button on Moodle. So, and I prefer that all your solutions be submitted there. Even if there are some handwritten pages that you will have to submit, I suggest that you convert that into PDF, okay, and then submit PDF form. Yeah.
Yeah, okay.
Okay, where were we? We were in this. Yes. No, I'll keep it because I want to use. Is this, if it's too small? Is this? Hide this solution, or I will. That's okay. I'm going to reveal all the solutions. Oh, this is big enough now. I mean the since I want to see both, I'm going to side by side, and I hope this is big enough for you. Is that okay?
Yeah, I think so.
Yes, sir.
Yes, sir.
Yes. Okay. So yeah. So this is the only one, okay, that I want to hide. Okay, you already saw it here. That's okay. So let's go through these solutions. No. Before I start and then discuss the solution for that thing, I want to say what are some of the legal execution before we get to this LTL formula satisfaction solution. I'm asking the question, what are some of the legal execution or traces, patterns of this transition system that you have? Okay. So by executions, I mean infinite paths that this thing can produce. So here are some infinite paths. By executions, I mean infinite paths. So starting from state 1, of course, we saw that you can go from 1 to 3 to 1 and then loop around. Okay. So that is here, I'm representing it as 132 to the power of omega. Okay. We will later introduce what are called omega regular languages. I don't know if you've already seen, maybe you're taking some other courses along with this thing where you're seeing omega regular languages. Have you? Any of you?
No,
I'm taking LAG.
Excuse me?
I'm taking logic, automata, and games, so it's covered there.
This is Ratnakar. Huh?
Yes.
Yeah. Okay. So nonetheless, you just for now, I mean, I'll formally introduce when, only later in the course, okay, when we talk about automata based model checking. So 132 to the power of omega. Omega means that is repeated that pattern is repeated infinitely. That's what it means. Whereas star in regular languages means finite, 0 or more repetitions. Omega means that it is, that's repeated infinitely. So that's what we have to do. So that is 1. So you can do 1, go 1, 3, 2, and then keep repeating that pattern. Or you can do 1, 3, 2, 0 or more times, followed by 4, 2, or 1, 3, 2, each of which 0 or more times. That pattern then gets repeated infinitely, correct? Because after doing 1, 3, 2, from 2, there is a non-deterministic. There are 2 choices you can make. You can either go to 1 or to 4. That's a non-deterministic arbitrary choice. And that's what is you could do. So you could have finite repetitions of 1, 3, 2 or 4, 2. You can choose arbitrary number between them, and that pattern you can then repeat infinitely to create infinite paths. Now, how about this one? Here I'm saying you start with a prefix, a finite prefix of 1, 3, 2, 1, 3, 2, 1 or more times, followed by 1, 3, 2, 4, 2, followed by 4, 2 repeated equal number of times. Is that a legal execution of a finite state system? Anyone? You see the difference between D and C, correct? Ratnakar, since you've already seen some of this, maybe.
Yeah, C requires that, sorry, D requires that there's an equal number of times every time you say one.
Correct. Okay, so that is clear. My next question is, if that can be simulated by a finite state transition system.
I don't think so, because you have no way of keeping track of n.
Yeah, that is right. If you do keep track of n, you could do, but that n that you can have a state variable in your transition system to keep track of that, but then that n, the value of that grows arbitrarily large, potentially, correct? Okay, so that's why, since we assume that if the state space is finite, then you cannot, okay? That is the idea. So see, because there are, so you can keep a stack, and then, that keeps growing, okay? It's kind of the difference between what you see as regular languages and pushdown languages, okay? Pumping automata, okay? So that is the kind of thing. So that's why what we say is the kind of executions, and that's why the kinds of properties also capture only those kinds of behaviors. So you cannot do D or E where you look at patterns where you need to count, okay? Where you need to be able to count. Now, if you fix a particular value of n, okay, that I'm only going to be counting up to 10 or up to some finite amount, then it's okay, okay? That you could encode it as using finite number of bits and so on. But to say that, okay, I will allow arbitrary n such that for n greater than or equal to 1 and n not equal to m such that n and m may be greater than or equal to 1, those kinds of things cannot be entertained, cannot be even modeled using finite state transition systems. They will end up requiring unbounded say. So that is kind of the restriction, and therefore, and since we restrict ourselves to finite state transition systems, are languages which are actually based on constraints expressed over the kinds of executions or traces induced by them. To that extent, will also be restrictive. So this, do you understand this? The rest of you, okay? Amin, yeah.
Yeah, I have a question. So we are stating that the execution mentioned in D, we cannot design a transition system that accepts only this execution.
No, the finite state transition system. That's what I mean.
Okay. Yeah, but this transition system in the left slide, it accepts this execution, right?
Yeah, it accepts this execution because the D execution is part of C.
Okay.
I mean, it's also there. I mean, in this, no. It accepts C, but not just the D. Okay, it accepts the entire C. Okay, all A, B, C, all are finite executions. But if you say, oh, I want to limit myself only to these, okay, then that's what you're not able to do. Okay. Yeah. So in a sense, what I'm saying is this is actually a property aspect of property. Okay. The executions, of course, this C, also, but you cannot distinguish. You cannot just constrain it to only accepting these kinds of things. Yeah. That's what I mean.
Okay, sir.
Sir, I have a question. Did we discuss the notion of acceptance for a transition system?
No, I have not. I'm not. Okay, so that's, no. I think I have not done it, but I'm giving this thing because one may ask the question, okay, sometimes, later on, we will see that, oh, these executions are only this kind, okay? So I want you to kind of appreciate, no, I have not defined acceptance, okay? But what I'm saying is because the acceptance, I have not defined acceptance because I have not discussed automata as a property specification language, okay? So, but when we say that these things are, even in logic, these kinds of things are not possible, is all I'm saying, okay? While C, you can have a formula that, okay, acceptance I'm not defined, but I've defined what it means for a formula to satisfy or not satisfy. Huh? So that is, so what you end up, so in these LTL and the temporal logic that I'm introducing cannot have these, you cannot have formulas that only constrain your traces generated by your transition system to be of this kind, okay?
Okay.
Yeah, so, I mean, when we see automata, the acceptance notion of what it means to accept such infinite paths will be discussed. But for now, we are already saying, oh, what are the paths that are satisfied, infinite paths that are satisfied by these things, okay? By these formulas, okay? That is where I'm saying, because of the way these operate, if you think about it, you will not be able to define formulas, okay, which constrain formulas whose set of paths that are satisfying will be of this kind, okay? That is the intuition that I'm trying to give you, okay? So because although I have not defined acceptance, we've already defined what each of these formula, the parts that are satisfied. Okay, so in that sense, XXY denotes a set of, and the formula XSY, its interpretation is a set of parts. Okay, and you know, you will see that this language, this logic already doesn't allow you to you know, do these kinds of you know, countings. And then I'm relating that to the notion of finite state systems. Okay, if you do allow for you know, the logic to constrain only to make that to denote only those sets of parts that are satisfied by these kinds of patterns, then you won't be able to do. That's all I'm saying. Okay, and that's okay for now for us, because after all, we are trying to express properties of finite state systems, and that is the relation I'm bringing. Do you understand, Ratnakar? I mean, the rest of you? Because there's also a relationship. You're not able to generate only these kinds of patterns anyway, if you're allowed to keep track of only finite state. Okay, you can ask, why not? Why? I mean, can I not write a transition system that generates only these kinds of execution patterns? That is the question I'm raising. Do you see what I'm saying?
Yeah.
Yeah. You know, for that, so you cannot. Okay. So you know, everything will have to be something like a regular language. You know, some you know, word in a regular language that is then repeated infinitely often. Okay, that's the kind of execution patterns, and that will actually, you will see, will exactly correspond to these logics, these kinds of propositional temporal logic that we have defined. Okay, because I sometimes get this thing. So when I say, oh, these infinite parts are of this kind, and then I always end up having a prefix and a tail, which is some finite pattern repeating itself. Some, you know, some of my students immediately ask, oh, why not? Why can't I have this kind of pattern? Okay, you know, then that, you know, that answers the question, because if you try to, you cannot even implement using a finite set of states, you know, things where those executions can only generate these kinds of executions, patterns. So that's what I'm, that's the intuition that I'm trying to bring. Yeah. Okay, so let's look at this XXY. So you're all convinced that those states from which every path originating from that state satisfies this formula is only one. I mean, that state is one. Okay, correct? Whereas states in which there exists some path that satisfies XSY is one as well as two. Are you convinced?
Yes.
Okay. XXR is empty. Why? For the for all thing.
There is no state for which from every single path originating from that state, you will necessarily visit one within 2 steps.
Yeah, within 2 steps. Okay, so that's because this is the only state. So if we start from here, So there is always a path, okay, after 2 steps that where it doesn't satisfy. Okay, but there are some paths from which, you know, at least for 3 and 4, so that after 2 steps. Okay, so that's interesting. Now, so let's get to this. Okay, Amin, so can you take a crack? And this we already saw. I don't want to repeat that. So this one, F, G, Y, or B. What are the solution? Are there states from which every path originating from that state satisfies this? First of all, okay, what is F of G? Okay, first, I'll ask you this. First, give me the states of Y. First, let's do this. So, Amin.
Like G of Y or B will mean something like every state in the path must be either Y or either B.
Correct.
Or,
Yeah.
then I think every path.
I mean, first, it says some states from which there exists such a path. Give me some path.
Yeah. That will be something like 4 and 2, the loop 4, 2.
So 4 and 2 repeating itself. So certainly there are some paths from 2 and 4, correct?
Yes. I don't think anything will satisfy for all conditions.
Yeah, that's correct. Okay, so you're right. You're right. So this one is empty. So now take a crack at this.
So when F is added, it means that eventually it should like reach to a point where
reach some you know, a point after which in every state Y or B has to hold.
Again, exist will be there, but I don't think for all.
No, give me some path. Okay, so I want to yeah. So give me a path where, see, this is a special kind of property, just like this property G of F of Y was something infinitely often. Okay, so that's the term that's usually used. So these are some interesting patterns that occur in practice, and that's why I'm giving names for this. Just like this is called eventually something happens, forever something bad never happens. G, there is a name for this, which is called persistence. Eventually forever, okay? That is what this means, persistence property. That is the name that is given. That is eventually something persistently becomes true. So give me an example of a path.
I'm not sure. Something like something starts from 3 and then keeps on looping it in the 2, 4 path.
4, exactly correct. Yes. So any path that ends up looping in only 2, 4, like for example, as B, okay? B paths that are of this kind, okay? So these are something that you end up repeating in 2 and 4, any such path. I mean, that could be 2, 4, something that is originating from 2, 4 itself and keeps looping, or it can originate from 2 and you know 3 or so, and then but it for some finite number of times it is loops in among 1, 2, 3, but eventually ends up repeating here. Okay, so that is what. Okay, of course. You know, if you're asking about the state from which every path for all this is still empty. Okay, but existencing thing, there is some path from every state. You agree?
Yes.
Am I right, or have I made a mistake? Okay. Yeah.
Yeah, it will be there.
Yeah. So this is persistence problem. Okay, good. So now what I want is to get to the next. Before I give, so now I want to take you through some CTL things. Okay. So let me, to make it interesting, so I have the solution here, but close your eyes momentarily so that I didn't. It's okay, even if you. Oh. Okay, so now I have some CTL formulas, okay, for which I want you to give. I'll go, I mean, CTL formulas are like CTL star formulas, so they are state formulas, correct? Therefore, you can't be asking what paths satisfy this. You'll have to say what states satisfy this. So there is no, it doesn't make sense to give for all and there exists. Okay. Yeah. So give me. So let's start. I want someone to attempt AX, AXY. Okay. This is actually corresponds to this. I'm just introducing, throwing in path quantifiers here. So let's start with Paramalai. AXY. Give me those states that satisfy this.
State. Every path originating from state 3 satisfies this property.
No. Answer me. Yeah. These are satisfied by those states. Okay, so give me the states that satisfy this. What you gave is a description. Every state any state that satisfies this formula is 1, such that every path from originated from that state satisfies XY. Okay.
Yeah. Then state 3 satisfies this. Because the next state will be
correct.
2, it will have Y.
Anything else?
No. 4. Yeah.
4. Correct. No? So this is 3 and 4. Obviously, 1 does not. How about this one? X of AXY.
State 1 will satisfy this property. Because state 1 goes to state 3 and state 3 satisfies AXY. And that's it. Only state 1.
You're right. So whenever you want to interpret this, it makes it, easy for you. So there, for interpreting LTL formulas, you will have to look at the path behaviors. So whereas in trying to do this, CTL. Okay, so it helps for you to keep this picture in mind. Okay, so let's keep this picture in between here. It's kind of same thing. So I will just sometimes this thing is impossible. Okay, so this is fine, good enough. I wanted to bring this thing down. Yes. So let's keep this. So, yeah, next, I want somebody. Okay, so Ratnakar, AX of EX, AX of EX of Y. So first starts with EX of Y.
I think 3 and 4. EXY.
Yeah, why? Because, yeah, I mean, give me an explanation too so that we'll kind of understand. So EX of Y, there must exist those states from which there exists a path in which X of Y should hold good. So in the next state, Y should hold good. So there is only one path from 3, so 2. And similarly, from 4, there is only one path. From 2, it does not hold good, okay? Because as a matter of fact, there are 2 paths from 2, originating from 2, 2, 1 that goes like this, and then 2. So in either of them, it is that case. So from 1 also, it's correct. So that's correct. So this is 3, 4. Now,
Should be 1 because 1 is the only state that has a path to 3, and there's no state that can reach 4 in one path. As in 2 can reach 4, but 2 doesn't reach 4 every single time in one path.
Yeah. So as a matter of fact, you can see there is a pattern. There is a YI. So what you will have to do is one way of checking CTL, and I'm giving you kind of the intuition. So you just find the get the solution for the sub formula. Okay. EX of Y, then it becomes AX. Then you will have to look at all those states from which AX, okay? Those states in which there are paths from which, in the paths in which X of that satisfies, okay? So the next state you will have to get to, must be those states in which all the successors are either 3 or 4, okay? That's why it is only 1. From 1, there is 3 or 4. Why not 2? Why not 2?
Every path from 2 doesn't necessarily.
That's right. Every path from 2 does not, because there is the successor 1, which is not in 3, which is not either 3 or 4. Okay, so this is also 1. Okay, good. So now let's get to what's more interesting is this one. Okay, let's ignore this. Let's get to AF of B. So I'll go back to Paramalai. So what is AF of B?
That will be all the states, because from every state we can have a path. that that will eventually go to B
Yeah.
from 1, 2, 3, and 4 from all the states.
Does it? So what does this require? That every path originating from that state, on that eventually B should hold good. So is it true for 1 and 3 and so on? Because from 1, there is path that can loop around like this, huh? On the left side here. 1, 3, 2, 1. So that never goes through B. So there are paths originating from 1, 3. As a matter of fact, from 2 also.
So then only state 4 will satisfy.
That is correct. So AF of B is only 4. So now do AG of AF of B. Question is for Parmalite, so you have to. What is this?
No state will satisfy. Yeah, no state will satisfy this property.
Yeah, because this is the only state.
Yeah.
So those paths. So there must be, and the only way that this can be satisfied is only by those paths in which 4 occurs continuously.
4 loops around again and again. But
yeah, so there are no that thing. So this is empty. Okay. So let's do. So next is Amin, EF of B.
I think for this, all the nodes will satisfy.
Correct, because they're all exist.
Yeah, there exists a path
that end up visiting 4 and then ends up there. Okay, that there is always that path from every state that that visits the thing. So this is 1, 2, 3. So now this one. Oh, I should have asked this. Pose this to.
This will also be empty, right?
No, I want you to do this. EG of EF of B. Okay, this, yeah. Yeah. So that's okay. So anybody can answer that. EG of AF of B. So if AG of AF of B is empty, EG of AF of B necessarily will have to be empty, correct? Who said empty? So that was Paramalai or Amin?
Amin.
So that must be empty. So as a matter of fact, you could see. So if AG of AF of B itself is empty, EG of AF of B has to be empty, right? So AG of AF is saying, oh, every path from that state, on that every state satisfies AF of B. So if that itself is empty, this has to be empty. So AG of AF of B is necessarily stronger than EG of AF of B. Okay, that's what I have indicated here. So that's why in this case this was empty. So EG of EF of B will be more liberal. I mean, AG of A will be stronger in the sense there will be fewer states. This will be a subset of that. Okay, so that is that's one observation. But what I wanted you to do was this one, AG of EF of B. Now that you identified EF of B, what is AG of EF of B?
Because EF of B has all the nodes,
Correct.
AG of E of B also will be like all the nodes.
Exactly right. Because any any path can only have these 4 states, and all of them they satisfy G. I mean, they satisfy G of F of B because they have to include one of those states. Okay, so that's. So finally, Ratnakar, so finish off. The other possibility, we already discussed AGAF, EGAF, EG. Oh, I've already done AGEF of B. So what would be EGEF of B?
AGEFB implies EGEFB, so 1, 2, 3, 4.
Correct. So this has to be,
1,
since
2,
that
3,
is already there, this has to be 1, 2, 3, 4 as well, right? Ah, no. Correct. Yeah, this has to be a superset of that. Huh? Correct?
Yes.
Yeah. So that's so this kind of gives you an idea, you see. That's why CTL operation. So see, LTL model checking, you will have to look at paths, okay? Whereas here you have to look at paths, yes, but there is a way to structure CTL model checking. And therefore, you can actually repeatedly use solve the problem for kind of a bottom up in that by looking at the tree of CTL formulas. So start with the atomic, the leaves, then collect the states for each subformula, and then use that to collect the states that satisfy the one level, the formula that is one level above, and so on. You may have to look at paths at each level, but but you could kind of structure it that way. And that's why you see CTL model checking is more efficient, okay? I mean, than LTL. So that's why LTL model checking, you have to look at paths directly and then see if those formulas are satisfied by sets of paths, and therefore this is a bit more complex. And this is just a precursor to what I'm saying, okay? So in general, what is the intuition? So let me go back to even if it's slow here, I want to do it in a particular order so that it will make sense. I hope you can read this. Okay, so now, so you've so far seen some examples where I've taken some formulas from CTL and LTL and then asked them to give me the meaning of that. But the other engineering, this is more useful and more interesting. Usually when you design systems and you want to verify it, you have to start, one aspect is modeling. The other thing is you will have to identify the kinds of properties that you want to verify. And then you have to convert them into the specification language, which right now, we are looking at temporal logic, especially 2 kinds, the CTL and LTL. Okay, or in general in CTL star. So, but normally what do you have? You have these kinds of things. So, so how do you? So I want you to look at each of these properties and come up with a CTL formula or an LTL formula, both versions for each of these. So the first one. So let's start with Ratnakar. So that's easy. So how do you express this?
How do I express this constraint in which language? Sorry.
What's give me a CTL formula as well as an LTL formula. And if you think they're not expressible, then you can always construct a CTL star formula, okay? Because LTL and CTL are sub-logics of CTL star. So first start with CTL and LTL. This is the property for this mod counter. Huh? I mean, you should be able to guess. Why is it taking so long? So I'm just saying it's forever S must be less than or equal to 3. So first look, assume that it is, what is it saying? When you say forever S must be less than or equal to 3, that means if you're saying on all paths, if you're looking at, if you're interpreting the behavior as linear behavior, so you're saying,
I got confused. AG S less than equal to 3.
yeah, that is CTL formula. Okay, AG of S less than or equal to 3, exactly correct. But it can also be written as an LTL formula as G isn't it? If you are, now I'm saying this is for transition systems, okay? So when you view it as, for if you're only looking at the linear behaviors, that is set of execution starting from initial states, GS less than or equal to 3, because LTL formula, when you consider satisfaction for transition systems, there is an implicit A. Nah? So therefore, this is in LTL, yeah, it would be G less with that condition, S less than or equal to, which is equivalent to AG of S less than or equal to 3. And every initial state, when you interpret it as a CTL formula, you would put it as AG, and then you will check if every initial state should satisfy this. When interpreted as an LTL formula, what you would say is, I will generate my linear behavior starting from any one of the initial states, and then see if for every such linear behavior, which are execution traces, that this condition gets satisfied. Are you okay? So do you agree? So this is, as an LTL formula, it is GS of S less than 3. Any questions there? See, because
I think it's fine.
Yeah, because you should view this now. I'm specifying these properties for behaviors for this transition system. So although LTL, the behavior is viewed as set of traces, I mean, when you're doing it, when you're asking, does this all linear behaviors of this generated by this model satisfies this? These two are equivalent, right? The model checking of when you check the model check CTL formula is the same as checking this LTL formula. That is the one that I want you to understand. If you have any doubts there, you have to ask me. Yeah. Okay. So that's okay. Let's move to the second bullet. Say, I'm going, I don't know in what order. Paramalite. Yeah.
CR has to be visible infinitely often. How we can mention it as for AG every.
Yeah, started with, we already saw some infinitely often. All you have to do is take that pattern for infinitely often and then couch it in terms of appropriate atomic proposition. That's what you have to do.
AGF S dot PC is equal to CR.
Give me first LTL.
It will be GF.
You're right. GF
Every,
of
S dot PC1 is equal to 0.
S
Yeah.
by
S dot PC1 is equal to CR. And yeah.
and the same thing, correct?
Yeah. PC2 is equal to 0.
Yeah, correct. Okay, so we come to Amin. Each process, no, how about the CTL version of it? Paramalan.
CTL will be, we have to append an A in front of both the clauses. AGF S dot PC is equal to AGF would suffice. Definitely AGF.
What?
AGF will suffice, right? Do we need
That's not
AGF?
CTL, is it?
Okay, okay. Okay.
If you do AGF, that is CTL star, but it is pretty much CTL anyway. Okay, I mean that is pretty much LTL, because LTL already has implicitly thing. So if you really want to express it in CTL, this is AG of AF. Okay, AG of AF. This and this one. So I'll ask Paramala again. Is this the same as above?
Yes, I guess.
So you think yes, Paramalai? Does anybody else disagree with him?
I don't think so. This is asking, this is saying that eventually the both processes will be in the critical section at the same in the
Right.
same point.
No, I mean, first of all, what this insists is that S dot, yeah, both of them have to be simultaneously in the same state, simultaneously, in the critical section, okay? Which doesn't happen anyway. I mean, it is asking that that thing should happen infinitely often at the same time, okay, on the same path. I mean, it is insisting that this event, where they're simultaneously in the critical section, should happen infinitely often. Now, this thing, yeah, that's what this specification means. So that's why, whereas here it is saying, oh, I should have this event happen infinitely often on all paths, and then it doesn't insist that there'll have to be. This is insisting the event that simultaneously they'll have to be taken, which for the mutex case it doesn't happen anyway, because you don't want this to. You want only exactly one process. Nonetheless, so we are discussing this independent of transition systems. So that's the reason this is not the same as that. Okay, so let's move to 3 and Amin.
This will be.
Yeah, you can split it. Okay, the consequent is already
Yeah,
done.
the same as the second one.
Yeah. So what all you have to do is to convert it into the thing, which is
The fair constraints.
yeah. So
Yeah, that will be something GF of S of Sj of turn equal to 0.
exactly correct. Yeah.
And
Here J will not be there because here I was
yeah,
using
S of
specialized predicate calculus, whereas here I can express it just in terms of the thing. All the temporal thing for which I needed to quantify over the indices here is no longer there here. Okay, so SDPC1 is equal to CR, and this whole thing implies this.
Shouldn't it be turn equal to 0 and turn equal to 1?
I'm sorry, yeah. So fairness is you're restricting yourself. It is equivalent to doing this model checking this formula, and with an implication on the original system. So in LTL, it is quite easy. Now, can this be expressed in CTL? Ratnakar?
Yes, just convert every G and every F to AG and AF respectively.
Yes. So what you're saying is, but when I do this, is that syntactically, I mean, is it within CTL?
I think so, right? Like I don't see it violated anywhere. We have two CTL formulas in the antecedent. We take their conjunction and then we do implies, and two CTL formulas in the consequent, we take their conjunction.
So let's see. So let's get to this because this one, see, here the reason that this is not exactly the thing is because think about it. So here you're saying, okay, every path that satisfies this, okay, once you do this, while this might be a CTL formula, but the meaning might be something different, okay? So it will only say, oh, for those states for which this thing happens, okay? So only for those states, okay? Whereas here you want the paths, okay? You have to constrain the paths. So if you think about it, this will not exactly be, because here I'm only constraining this thing is on states, correct? So this one is a separate formula, which is, for those states for which this thing holds good, then, you look at, you need to check these things. So,
But if this holds true for the start state, isn't it the same thing? Which if this holds true for the start state?
Yeah, I think okay. Let me get to this after the thing. So in general, the because you will, that's actually not true, because when you take the negation of these things, there are some uh, constraint. Yeah, okay. So this is not as simple as that. Okay. So in general, the CTL, because they are, I think the meaning will not be the same. Okay. Let's see. So why that is so? So you're right. That's a good question that you have. If it is, if every if the initial state satisfies, if every path from the initial state satisfies this, then oh my, for those paths, okay, why is that not the case? Okay, missing the argument here. If you take the negation of this, so let's revisit this after I go through, which I will do in the next class, some equivalence of formula, and then taking negations of CTL formula and so on. Okay, but to begin with, okay, so let's move to, so okay, so here is the claim that in general these kinds of restricting to certain parts, the semantics will not exactly coincide. Okay, and we will get to that. There will be one full lecture that I'll be devoting on expressing fairness and so on. So I'll get to that. Before that, I need to cover some equivalence and so on. But to finish up this thing, so let's move on. So I'm claiming that in general, this is not going to be the thing. Okay, fairness constraints itself cannot be expressed in general. Okay, within CTL, and therefore fair model checking in the presence of fairness constraints will have to be dealt with in CTL, differently. Okay, but let's finish up this thing. So let's go to number 4. And this one was for parameter. So here there is some branching behavior that I'm asking you to express. Okay, so obviously some of these you may not be able to express in LTL. So what does the first one says? Can you take a crack at that, Ramlan? So what does this thing say? For
There exists a path whose first state is S0.
correct. Yeah, but that is the initial state. So that you could leave it because that is implicit in the model checking, no?
Yeah.
But here, for every state, there exists initialized, and what I'm saying is,
Eventually, in every path, AB will be 0.
yeah. But this itself is like an F-like property, no? So that is not that difficult. So all I'm saying here is, what am I saying here? F of, I thought that I had specified some more interesting property. Okay, and I think that neither of these things. This is actually f ab of 0, isn't it? Nothing more than that. All this extra paraphernalia is there only to say that paths starting from an initial state. Correct?
Yeah.
Yeah. So that's not that that interesting. So let me take the maybe there were some things in my who's that? Isn't this? Ah, yeah. Anyway, discussed lots of these things. So, but I've already given those things. Okay. So I don't think I have any good examples. So I've already given you all these things. So let's. What else did I want to do today? So what I want to do today was. So let me in the 15 minutes I have. Let me discuss the equivalence of formulas, which is there in this one. This. Should I start with that or general thing? No, I think I will start with the equivalence formula next time. So let's, since we are discussing the semantics of these formulas and so on, so let's stick to this one. Just to, I think you've already understood this thing. So just to contrast these 4 different things, okay? So what is happening with AG of AF of P, okay? And this is actually wrong. And so when you look at AG of AF of P, in the general context, so you have these kinds of things. So when you interpret the CTL or CTL star formula, you will have to do as you've already seen, that you have to say, oh, for all paths, then you have to kind of change your view in terms of paths as well as states. So what AG of AF of P, the pattern that comes is that on every path, the branching path, that on everything you end up some point at which crossed points here are P. Okay, so you have these kinds of frontiers. Okay, and at every frontier, at some point, in the frontier that there must be a cross state before it loops back into something, into a state that you've already seen. There must be some crossed state. Okay, so that's what this thing says. Whereas EG of AF of P is all it requires is that it does not say there must be one path in which that there is some you end up this looping back, and the cross state inside that loop will have to happen only on one path, not on all of them. So here it is enough if there is, okay, on this path it happens infinitely often. On these things, it maybe AF eventually P will hold good, but they don't have to happen on all these paths. They don't have to happen infinitely often. That's why these crossed one will not have to be as part of a, part of a loop. Okay, so that is the difference. And whereas for 2, a g of ef of p is kind of indicated in this situation. So here, on every path, it has to be globally true that every state there has to be, they only need to exist one path in which P holds good. So for example, here, so here, if you look at it, so there is this path on the left side. If you look at that, that's a path on which none of the states, that's on which, yeah, this is a situation which violates AG of AF of P, but for which AG of EF of P holds good. That's because, you see, on the leftmost path here that I'm moving my cursor over, there is no cross at all. Okay. Therefore, but from each of those states, there is one path in which P eventually holds good, like I'm doing here. Okay, so whereas, and that's why this satisfies AG of EF of P, because it violates AG of AF of P because this particular state does not satisfy, because there is a path in here in which P eventually never holds, although each of those states satisfies EF of P. Okay, and that's why AG of EF of P is different than AG of AF when I replace EF of P. Is that clear? So that's why these are, I mean, I put some implication here. This is actually wrong. Okay, I claim this is wrong. In the next class, I want you to think about it, why I made a mistake here, because I'm trying to explain the difference. We already saw that EG of AF of P is certainly, AG is weaker than AG of AF of P. But AG of EF of P is different. Why it's different is what I'm explaining here. So is that clear? So do you have any questions there to see what the difference in general, what I'm saying? Why AG of EF of P is different than AG of AF of P. And a counter example to that is what I'm giving here. Is that clear? Why this one here, the behavior that I've shown here, does not satisfy AG of AF of P?
I lost my connection for a minute in the middle. I just wanted to ask, I don't know if you've already said this, but does that mean by mechanically replacing GF with AGAF it works? Or like it will not work for others, but for AGAF, does it work?
No, it'll work what? No, I didn't understand your question.
Okay, suppose I want to convert an LTL formula to
now we'll get to that. Okay, first, that is the result that I come towards the end here. But before that, I'm just comparing two CTL formulas. Okay, before I do that, now I want you to understand why AG of EF of P is different from AG of AF of P. Okay, that is what I was trying to explain. Okay, whereas here, this means that all the frontiers I'll have to have, and every path, originating from that initial state, I have to have a cross thing in here. Whereas I'm showing, whereas AG of EF of P does not require that. Okay, it only requires that every path globally should be such that every state in that should be such that there exists one path on which F of P eventually P holds good. And that's what is happening here. See, I have set it up here such that there is a path in here in which every state indeed satisfies
Understood.
EF of P, okay, but there is a path, sorry, what I'm saying, yeah, so you understood that, no? So while eventually P holds good, there is, I'm getting confused myself here. I have to be, yeah. So AG of EF, yes. So whereas what's happening here is AG is coming here. So what this requires, what this requires is on every part, I'm correct. So it has to be such that on every state, it has to, I mean, every path from, every state will have to be such that eventually P holds good. But here you see, the reason that AG of A of P does not hold good here is because this particular path from the initial state, okay, on that, that every state does not satisfy AF of P, although it satisfies EF of P. Okay, that's the point I was making. Because the reason that it does not satisfy every state on that path does not satisfy AF of P is because this path itself on the left side will not have a cross at all. Okay, that's the difference between having an AF and an EF. Okay, so now finally, similarly, the difference between EG, this AF and having an EF. Okay, whereas EG of AF will require there must be one path in which every state, every state is such that every path or every path originating from each of those states, P will hold good, whereas this one requires only one. So even if one, I end up, there exists a path. So for example, here, there might be states here in which P never holds good. So for example, there can be path in here where P never holds good, but as long as there is one path. Therefore, EG of AF, EG of AF is slightly more stronger than EG of EF, but they are not comparable, and that's what this thing says. Now, coming to, I'll end by coming to addressing what Ratnakar asked. Now, the question is, we kind of saw that getting G of F is, normally it seems like if you started with all a CTL formula in which you only have universal quantifiers, then or you start an LTL and you want to get a CTL formula, it seems like you can put A around it. Okay, it's not as simple as that. Okay, but what you have is the following result. Okay, and that you can use sometimes to kind of compare CTL and LTL. What this says is, so here is the result. Let phi prime be an LTL formula obtained by dropping all the quantifiers from CTL formula phi. If after dropping such a formula, if the two formulas are equivalent, if they're equivalent, of course, then you have found a corresponding LTL formula. But if they are not equivalent, then it turns out that formula phi is not expressible in LTL at all. Okay, so there are two things that's happening here. Okay, this is in general for any quantifiers, A as well as E. So you just have to drop the quantifiers. This you could use for going from CTL to LTL. You drop the quantifiers and then check or argue get a proof, okay, if they are equivalent or not. Okay, I know I have already defined what it means to prove equivalence of two formula, that they'll have to be equivalent on all these things. If they are not equivalent, then after dropping the quantifiers, if those two are not equivalent, then you might as well give up finding an LTL equivalent to it, because this result says that such an LTL formula is not even expressible in LTL. So this is a bit trickier than just dropping quantifiers. After dropping quantifiers, you will have to check if they are equivalent, which means if on all behaviors, if they are if the two formulas for all transition systems, if they are equivalent. That's how equivalence of formulas are defined. And therefore, you would think that CTL and LTL are somewhat incomparable. You would think that CTL formulas, because it has both universal and existential quantification over parts, and LTL formula does not have. There are several instances where an LTL formula, a property that is expressible in LTL, cannot be expressed in CTL. So we will see these things a little bit more carefully in the next class, and also revisit this one question that Ratnakar posed about expressing fairness. Why you won't be able to express all kinds of fairness constraints within a CTL in the next class. Okay. So what I want you to do is I want you to study these slides, and then make sure that you understand the difference between these four versions of CTL formulas, and and why, and also why they are they are not the same. Okay, they are not equivalent, and also why when you drop the quantifiers, why G of F of P is not necessarily equivalent to any one of these 2, 3, or 4. Okay, whereas it is equivalent to AG of AF of P. That as an exercise, I want you to do as a class exercise. In the next class, we will discuss more closely all the expressive power, relative expressive power of comparing CTL and LTL in the relative expressive power, and also visit this question of expressing fairness within CTL, which is a bit problematic. Okay, so those two I will get to in the next class. Okay. Yeah, any questions before I end the class? Okay, if there are no questions.